Okay, and we're live. Sorry about the technical issues there. I don't know what happened. The scheduling on YouTube was a little screwy. I think, as I was telling Ishan, I was overseas and I accessed this overseas, and I think my time zone setting got messed up in StreamYard. And then, anyway, and I only just noticed it and then had to switch everything around. So that's my story. I'm going to go stick with it. But thank you all for joining. We've got a really fun kind of end of the year presentation here, all about LLMs. But before I turn over to Ishan, I'm going to do a quick little intro because, first of all, I have to thank my sponsor. I have one sponsor right now that helped me kind of keep all these events for you free. As you all have who've been here before know, we run a ton of free sessions all throughout the year, both presentations and live coding and free conferences and all that. And the sponsors are how I'm able to do that. So I want to give special thanks to Netlify, who's been a sponsor of mine literally since when I started this site and when I did the first events. They've been around, and they continue to sponsor. And they are a great place if you want to deploy your applications, full stack applications, Next.js, Astro, whatever it is. I actually deploy the site on Netlify, so I highly recommend them and check them out. And thank you, Netlify, for being a sponsor. So I don't have any upcoming. If you've been on the site, you'll see I don't have any upcoming events listed yet. I do have things in the work, as always. I'm still trying to kind of figure out what events we're going to do in 2025, but I can tell you for sure we already have scheduled. The jam.dev is coming back, more serverless is coming back. All of these events, the conferences that were there last year are all coming back in 2025. We have dates set, and those will actually all get posted soon. So look for more details on that. So we got, I think, 4 or 5 conferences throughout the year. And Ray will be coming back with Code Break. So new episodes of Code Break every week, every other week, with Ray Camden. And Nick will be coming back with his Too Full to Stack. He usually does that once a month. And I know Dev Relish, if any of you are fans of Dev Relish, it's been a kind of on hiatus for a little bit, not intentionally, but that's just the way life works. Sometimes I've been busy, Aaron's been busy, so but that will be back, I expect, soon as well. So plus we'll have more presentations coming and all that stuff. So please stay tuned. And if you really, I love to hear from you. If you've enjoyed CFE, I put a lot of effort into this. And it's not, I mean, technically a business, but it's like not really a business. I mean, most people think of a business as something you make money at. This is a business that at least sustains itself. So but I just love doing this stuff for the community. And I hope you enjoy it too. So if you got any feedback or want to speak or you want to sponsor, you can please reach out to me at brian@cfe.dev. I'm always open to feedback. Yes, this session is being recorded. You can obviously watch the recording that you're here at right now. You can watch this as soon as it's over. I will also be editing it down so you don't have to hear me do this whole intro spiel and others, and any kind of other things that need editing out. And that will be posted probably by tomorrow, if not by or by Monday. So look for that as well. And then you can also find all of our recordings on cfe.dev. In fact, there's like 350 plus recordings because I've been doing this for like 8 years now. So there's a lot of recordings going back. You can learn just about anything. And if you want to remember what we were doing 8 years ago, that's even kind of fun. You might see how much things have changed, or not. So yeah. You can go back in our archive and find all the old stuff. So you can follow us on all the socials except for the bad place. So you can find me on Mastodon, on Discord, on YouTube, LinkedIn, and Threads. So that's it for my intro. Since you all didn't come to hear me talk, you came to learn about large language models and how they work. And so I am going to actually turn it over to Ishan, who is going to teach you all about that.
Okay. Thank you, Brian. Thank you for having me. Welcome to Inside the Brain of a Large Language Model, how it works in 30 minutes. So I'm here to tell you, when you are building with AI, the most important model isn't the one in your code, it's actually the one in your head. Your mental model is really the most important, because the better your mental model, the more effectively you're going to build. This isn't new. If you're used to writing native applications, you need a mental model of how the CPU, the RAM, and the disk work. If you're doing web development, which we do a lot here at CFE, then you need a mental model of the browser, or maybe the box model if you're working with CSS. And what I'm, here to tell you, no surprises, I think one of the most important mental models you're going to need going forward in the future is AI, simply because it's in everything. So you need a mental model of how the large language model works. The problem is, if you want to go beyond just these kind of, high level analogies, there's a lot of complexity. There's a lot of, uh, you know, technical gatekeeping, it can feel like, where people are like, well, you need a semester of calculus and a semester of linear algebra and then a semester of machine learning. And it can leave you feeling like a deer in headlights. And I'm here to tell you, it doesn't have to be that way. Um, I know that because I teach a class online where basically in about 1 to 2 weeks, we take people from knowing almost nothing about how the models work to actually seeing every single step of the model in complete detail. And that brings me to who I am. So I'm Ishan. I'm probably best known in the AI community for Spreadsheets Are All You Need, which is an implementation of GPT-2, which is a large language model from OpenAI that they open sourced in 2019 and a precursor to ChatGPT. I wrote it entirely in Excel using pure Excel functions, no Python, no API calls. But the most important thing for you is that if you are, upskilling or retraining on AI, I have been where you are. I have been a traditional software developer up and down the stack, whether it was device drivers to native applications to cloud and web development. I have been a technical product manager at an enterprise B2B company. I have been a technical leader. I was CTO at a startup. In fact, that's where I got to know Brian through our work with him there, where I was CTO at Layer Zero. So I've been where you are, and I'm here to tell you, you can do it. If you know just a little JavaScript, as we'll see today, you've got the foundation to understand at least a sharper mental model than maybe you've been told you can get. So what we're going to do today is we're going to go to AI med school. We're going to operate on our patient. Our patient is going to be none other than GPT-2. And that is a large language model that was open sourced by OpenAI. They built it in 2019. But don't let that date fool you. When it was launched, it was state of the art. In fact, it was considered too dangerous to release. But more importantly, if you think about all the large language models you probably are familiar with, like ChatGPT, Llama, Gemini, Bard, as it was previously known, GPT-4, and Claude, they are all of the same family of large language models that have a common ancestor, and that is GPT-2 is basically their granddaddy. So if you understand how GPT-2 works, you're basically 80% of the way there to understanding how the more modern models that you probably use day to day actually operate under the hood. Now, when I've done this talk in the past, I've done it in Excel using a spreadsheet. And the way the spreadsheet works is you type in some text here on the left, and then here on the right, you get the predicted word. But today, what I'm going to do is I'm going to use a spreadsheet in the browser that I have built using web components. You can go to it right now. It's spreadsheetsarallyouneed.ai/GPT2. And in fact, here it is right there. And if you scroll down, the first thing you're going to want to do is actually read or watch this video. It'll show you how to load the model weights. So it'll say ready, all model parameters loaded. You have to download a file and then upload it into your IndexedDB database. But at that point, everything is running locally in your machine. And the benefit of that is it means you get to debug it using DevTools Inspector, just like any other web app. So the way it's structured, let's go back to the slides here. As you can see, is there's a series of cells, right, like this. And you see there's two types. There are these code blocks that you can edit. and you hit a play to run them. And then we have these sheet blocks. So let me go to this one, which I've already run. And if we go right here, you can see it runs a function if you hit play, and then you can see the result of that function. So we have a web component called a cell, and that's just a wrapper for every single UI element. It gives us this play button and some other controls to run all the way to the cell. And then we have our sheet elements, and they execute some mathematical formula just like you would in a spreadsheet, and then displays the result as a two-dimensional table. And those are wrapped by the same cell component up here. And then you give it an ID, so other formulas can reference it. And then you give it a formula. Like here it says, get the matrix, call matrix last row function, and then it gets it from this other table, which is called, or sheet called block step 16. Now that's the DOM ID of another table on the page, and it will just simply fetch that. That's what the bracket means. Go grab the matrix over there, and it automatically knows the matrix height and width in order to do any type of computation. And then you might be wondering, well, where do all these functions come from? They come from you, or they come from JavaScript if you're a web developer. These are the same code elements. So that looks like these right here. Let's scroll up. So something like this. Prompted tokens is right here. You can see that function is defined, and then it's basically calling it right here. So all the mathematical operations that the sheet does to execute GPT-2 are there. Every single thing. The matrices themselves are two-dimensional JavaScript arrays. It's built as a teaching tool, so it's very straightforward. Even matrix add and matrix multiply is right there. So there's nothing here that is obscure. There's no layers of abstraction to get in the way. And the way these work is basically, again, you have a cell with an ID, and then you just have a script block where you put JavaScript in, you put text plain so the browser doesn't execute it. Then the framework pulls it out and executes it when you hit the play button. And that's basically how it's structured. But again, the cool thing about this is that it's very native look and feel for debugging if you're a web developer. So let me just show you a little bit of that. So let's go to one of these cells. Let's go to separate into words. So I'm going to run to this cell, and you can see it just executed all the cells before it right here. And then it ran this separate into words function. I'm going to go here, and I'm going to open up my inspector, and let's do the following. So one thing you can do is you can console debug. So console log matches. So I can see what that looks like. So I hit play. I've now redefined that function. I'll run it again, and we can see right here in WebKit Inspector, I can see that actual variable. I can put any debugging statements everywhere I want, and I can just watch that that inspector window as it's running the model. But we can go even further. I can do something like this, and I can just say debugger, and then redefine the function, and then run it, and boom, I'm right here in my inspector debugger. I can step through this model because, I don't know about you, but sometimes I don't really understand code till I walk through it. And I like to say this lets you debug your thinking. That's one of the great things about having the model so accessible and manipulatable. That's how you build a mental model, is basically by interacting with something. And then you can step through it and just use the same inspector you're used to using. And let me just remove this debugger statement so it doesn't break something or slow something down if I need to use a demo later on. Okay, so that's the power of having this in the browser, making it really accessible to those of us like myself who have a web development background originally, rather than an artificial intelligence background. So today we're going to do 3 things in our AI med school. We're going to take our patient, GPT-2. We're going to study their anatomy, understand what makes them tick, and look at all the different parts that make up the model. Then we're going to take our patient and we're going to put them through a virtual MRI. And then finally, we're going to actually perform brain surgery on our patient, and we're going to change its thinking without even changing the prompt. Okay, let's get into anatomy. So what is a large language model? So a large language model just simply takes some input text and outputs the next predicted word. Technically, the next predicted token, which we'll talk a little bit about, but it just outputs just one thing, which is the word. So when you go into, say, ChatGPT or Claude, and it outputs a paragraph of text, what it's doing is it takes some input. In this case, Mike is quick, he moves, and then it just predicts one word after it says quickly. And then it takes that word and it sticks it back to the input, and you get a new input, which is Mike is quick, he moves quickly. And then you run it through the model again, and it says, oh, the next word is and it keeps going. This is an auto-regressive model, as they say. But the key point here is the core function of the model that you need to understand is just how it predicts the next word. And then you basically understand every step of the model. And so the spreadsheet or web page right here simply predicts just what the next word is. And if you want to see paragraphs of text, you take that word, put it back into the prompt, which is right up here, and then rerun it again, and you'll get the next token. Okay, so we said that, large language model like ChatGPT or Claude is trained to complete sentences like this one and to fill in the blank. Mike is quick, he moves. And as a human, you probably understand intuitively like what a likely completion would be. So he moves quickly, maybe he moves around, maybe he moves fast. But how do we get a computer program to do that? Well, here's a fill in the blank that I think you'll have no surprise that a computer can do really well. 2 + 2 = 4, because it's a math problem. And computers are really good at math, even if we make the computation really, really complex. So in effect, what researchers have figured out how to do is take what is a word or language problem and turn it into a math or number problem. In order to do that, they have to do a couple things. First, they need to take the words and map them into numbers. Now, here in this slide, I've simplified it. I show each word going to a single number. In reality, as we're going to see, it's going to be a long list of numbers called an embedding. So we break the prompt up into tokens, and then we turn those tokens into embeddings. That gets our words mapped to numbers. But basically, it's just simply how do we map the words to numbers? Then we do a bunch of number crunching on them. This is where you might have heard of attention gets factored in. And then we have a multi-layer perceptron, which is another name for a neural network. They go through 12 passes together in order to finally come out with a mathematical number result. Now, that is going to be an approximation. It's a number that isn't going to cleanly map back to any one single individual word. What we're going to do is we're going to say the words that are closest to the number that we get out, predicted out of all this calculation, will give those a higher probability. And the words that are further away from whatever number we get, we're going to interpret as a lower probability of picking that. And then the model will just simply sample from that distribution according to that probability. And that's the job of the language head. So we get this diagram for how the model works. First, we take in text. Then we take that text and we break it apart into tokens. These are subword units we'll talk a little bit about. Then we map those tokens into numbers called an embedding. And then we do a bunch of number crunching. And then finally, we reverse the process. We turn the numbers back into text and we get out our next token. So let me walk you through what each of these steps are in just a little more detail. So the first step is tokenization. We split the word, or the prompt rather, into a series of tokens, not necessarily into words. So in our test sentence, we've got Mike is quick, he moves. It turns out that every single word in this prompt maps very cleanly to a single token, but it's not uncommon for a single word to map to 2 or more different tokens. Let me give you an example. So let's go back here and let's change our prompt instead of Mike is quick to Mike is flavorize. And then I'll rerun to here. Let's see. Did I spell that right? Oh, that's not the separation into tokens. That's why. Let's go to here. Okay. So let's see if I blow this up and let's close this. There we go. So you can see right here at final tokens, this is just the final of the tokenization process. It broke up the word flavorize into flavor and IZE, so as 2 separate tokens. 2 things to note here is that the word flavorize isn't even in the dictionary. So we're kind of illustrating that it can handle words that it weren't even planned for. The second thing is that it did map flavorize to flavor and IZE, which is kind of what you would expect as like a human intuition for how you'd break the word. But the algorithm under the hood doesn't map always cleanly. It's kind of a happy coincidence when it does. And it does find a lot of common, suffixes, but isn't really the same thing as the linguistic morphemes, as they're called, the little subwords, parts of speech that humans use. And it's worth noting that this is not a naive kind of parsing. So A great example of this is if you take reindeer and re-injury. So let's run that. Okay, so reindeer is R-E-I-N-D-E-E-R, but re-injury, which also starts as R-E-I-N, is rain and jury. So it doesn't even map to how you would think of it, like re-injury. It's a good example of something not mapping to your human intuition. So it's a compression algorithm. It doesn't always cleanly map to your intuition, but just know it's going to take your input text and break it apart into these subword units. Okay. Next up is the embeddings. So this is where we take our tokens and we map them to a long list of numbers. In the case of GPT-2, it's 768 numbers. Larger models used today map it to even more numbers. And every single token gets the same number of these numbers. So even the period here gets 768 numbers. Let me show you that. So let's go here. Let's go to token embeddings. So here are the token embeddings for, well, let's use Mike is quick. So token embeddings. There we go. So here are the token embeddings for Mike is quick. I've added some labels here so you can see which row corresponds to which token. But this row 1 right here is all the 768 numbers that map to Mike. Here's period. And you can see if you go here and I go to row 1, column 768, and you can see there's my 768th column. That's where it ends. So every single one of these is 768 numbers long. And that 768 long array is supposed to convey the meaning of each of these tokens. What does that mean? Well, probably in the time we have here, the best way to conceptualize it is like we're creating a map for words. And we want to put the related words closer together. So, think of words like happy and glad. They're both happy emotions. We'll put them here. Sad isn't a happy emotion, but it is still an emotion. So maybe it's sitting over here on the island. And dog and cat are animals, so they're not really emotions. So they're over here somewhere else on the island on the other side. And rather than this being a two-dimensional map, we're putting all the words together in, it's a multi-dimensional map. So in the case of GPT-2, where we have 768 of these numbers, you can think of these as positions inside that map, coordinates, that just are putting them in a 768 dimensional map, putting the related words closer together and the unrelated words further away from each other. Okay, so that's text and position embeddings. And then we get into the heart of the number crunching. These are called layers. I like to call them blocks to remove confusion with the layer that's in the multi-layer perceptron, which we'll talk about in a second. And what happens in here are two key steps. Inside the spreadsheet and inside the web page, you'll see there's actually 16 steps. I'm going to simplify it a lot for you here, though. The two biggest ones are attention and the perceptron. So attention is where the tokens talk to each other and get a sense of the larger context and meaning of the prompt that they're in. So hypothetically, he might look at Mike because that's the antecedent to its pronoun, or moves might look at quick in order to disambiguate the word because, for example, quick has multiple meanings in English. It can mean moving fast in physical space. It can mean being smart, as in quick of wit. It can be a body part, as in the quick of your fingernail. Or it can actually mean alive or dead in Shakespearean English, hence the phrase the quick and the dead. And so the fact that the word moves is in this sentence, or in this prompt rather, helps the next stage, the multi-layer perceptron, understand that when it tries to make its prediction as to what the next token is going to be, we're actually talking about this first definition, moving in physical space. So it could predict quickly, it could predict fast, it could predict around, but it's certainly not going to predict something about your fingernail because moves is there and present. Now, what does it mean for these tokens to talk to each other? Again, it goes back to embeddings. They're basically sharing subspaces of their embeddings, or actually transformations of their subspaces of their embeddings to each other in a very kind of complex way that we go into more detail in the class. But no, conceptually, they're just kind of sharing information with each other and kind of disambiguating the meaning like we're doing here with quick. And then we repeat this process. We take the output of one block and we put it back into the output of the next block, and we repeat the process 12 times. Then finally, we get to the end of the stage. We get to the language head, where we basically pick the token and output it. Now, the way this happens is the output of the very last, the 12th block, is a predicted embedding. We take the embedding of the last token, and that is a prediction for what will complete our fill in the blank. But this predicted embedding, we have to map back to words. And it's not going to map cleanly to every single word. What we do is we take the words, or rather tokens, that is closest to in this map, this embedding space, and we give those a higher probability. And the ones that are further away, we give them a lower probability. And then your LLM model runs a random number generator and picks one of these according to an algorithm called a sampling algorithm. Now, in the case of the spreadsheet and in the case of the web page that you guys are going to be using, I've implemented the simplest. It's called greedy or temperature zero, which is I simply just take the highest probability word and I output that. But in what you're probably more used to, they're using a much more complex sampling algorithm. They might be doing something like top K or top P or beam search, where it actually tries to walk the tree of all the different possibilities and pick the most likely. And they're even more complex samplers than that. Entropics is a really interesting one to take a look at if you're curious. But the key thing is the most of the randomness you get out of the model comes from this stage and how it's picking the next token. And this is where this temperature parameter gets used, because that changes the distribution and allows the lower probability ones get more of a boost in probability than they normally would. And that's what temperature is really doing. It's just altering this probability distribution, although it's sometimes described as being more creative. Okay, so this gives us back to our diagram. We get text, we turn the text into tokens, we turn the tokens into numbers, we do some number crunching, and then we get numbers into text, and then we get our next token. Okay, let's talk about imaging and putting our patient in a virtual MRI. While we're doing that, let me set something up. Because I know it's going to take a second to load. Okay. Let's get into another interpretation of the large language model. So I showed you this diagram of the large language model as a series of 5 to 6 steps where 2 of them get repeated very often, which is the multi-head attention and the multi-layer perceptron. We can actually interpret the model as a communication bus, where we look at the tokens, each in the prompt, like in this case, Mike is quick, he moves, as actually a communication channel, where the multi-head attention and the multi-layer perceptron are actually components inside this communication bus that are communicating with each other. So the multi-head attention is basically moving information between the tokens, right? We talked about them sharing. And then the multi-layer perceptron looks at every single token and tries to make a prediction. So it only operates on its part of the communication bus. And what we can look at this is as the model across layers is actually communicating, where the attention of one layer might be sending signals that actually get interpreted by the perceptron of yet a different layer. And the way we can get a view into this is a technique called the logit lens. We take that last step I mentioned, the language head, and we actually stick it in between every single layer to see what its output is. And we ask, what was it going to predict if we had just stopped the processing here? So there's 12 layers in GPT-2. If we had stopped at, say, halfway through at the 5th block, what would the prediction have been? And then we actually look at what the results are. So let me show you kind of a feel for this and what it looks like. So right here is a version that isn't quite ready and published yet on the website, but it's very much the same as what you saw here. So on the web, and I'm going to go to the very end of this. So it's actually showing me for this Mike is quick, he moves, what the next top 7 predicted tokens are. So quickly, fast, like, around, his, with, very. Basically just changed this function here in code for predicted token. Instead of grabbing the largest value, which is what this guy does, code for predicted token, just grabs the max logit and its index and then just simply returns that. This version actually goes through and grabs the top 7 and then outputs them in order so that we can see what they are. Well, we can ask, we can see that quickly was the most likely, fast is the next most likely, but we can say, well, what happens if we ask the model what the next predicted token was after halfway through. So we can go right here. And the other thing this version of the code does is it saves the information in between the layers. These are called hidden states inside a global variable. And as a web developer, you know where hidden states usually live. Sorry, global variables live on the window object. So window hidden states. And since we're 0 index, we'll go 5 to get halfway through. And then we just rerun these. So let's rerun that, rerun that. We don't have to refetch those variables or those weights. Run the predicted embedding, rerun the multiplication to get the logits. It'll take a little bit of time, 1 to 2 seconds to do that matrix multiply. And then we're going to get the predicted token out. Okay, so here you can see its predicted token was forward, back, up motion. So if we had stopped halfway through, it thought the right answer was, Mike is quick, he moves forward. Not bad. Quickly is actually here, but it's just not high enough in probability to make it to the max. So let me show you an example of this right here, which is with a different prompt. Here we're going to go back into Excel for a second. One note about the spreadsheet and partially why I built this in the web browser is that Excel on the Mac will lock up running the spreadsheet. So I actually have to run it inside Parallels, which leads to some graphics issues. So first of all, the prompt I'm using here is different from the Mike is quick one. It's if today is Tuesday, tomorrow is, and the next predicted token is Wednesday. Now, GPT-2 gets this job right for all 7 days. It knows what the days of the week are and how they're related. So if you change this to today is Thursday, it'll say tomorrow is Friday. And so you can see, let's see if we go here. This is kind of a table I've built out of the same results you saw here, where what I'm doing is I'm taking at each layer, what is the next predicted token? So right here, if you had asked what the next predicted token is after the end of the third block for if today is Tuesday, tomorrow is, it would have predicted not. So one thing to note is that when we make a prediction, every single token is trying to predict what the next word after it is, even if we already have the word in the prompt. So for example, if today is that token is trying to predict the next word after it, even though we already have it. So it was saying if today is, it thought at this point, the next word would have been night. But if you scroll down at the end, we get our final result. So it said, if today is, it thought the next word is the. If today is, then something the. If today is Tuesday, it thought comma would be the next predicted thing. It turns out in this sentence, comma is the right next thing. So that's how to interpret this. So each of these sections here separated by blue is the output results of each block. And what each block thought were the top 7 most likely next words. So the key thing I want you to note is the right answer we know is Wednesday. Where is it? Well, it's right here, right after Tuesday. And it makes sense, in that embedding map for words, Wednesday probably is pretty close to Tuesday, but then it completely disappears. And then it pops up here, but it's not the highest probability thing. And then it's slowly moving up in probability until it locks into place. In fact, we don't even need the last few layers. Okay, so what the heck is going on here? Well, a bunch of researchers use this technique called logit lens on steroids to figure this out. And they wrote this really great paper called Mechanistically Interpreting Time in GPT-2 Small. They later turned to a paper on arXiv called Successor Heads. But what they found is there are only 4 components that are doing most of the heavy lifting of figuring out what the next day is. And it's called the next day circuit in GPT-2 Small. And the key components are the perceptron from layer 0, the attention from layer 9, the perceptron from layer 9, and the attention from layer 10. And it's a great example of a circuit created by the model to accomplish a task. So the key takeaway here is that the model effectively has a toolbox in each layer of components that can do different types of jobs. And when it's trying to solve a problem, it's almost dynamically on the fly or during training figures out for a particular job it's trying to solve, how to put those components together in a circuit to predict what the next token is. Okay, now it's time for surgery. You probably are familiar with Golden Gate Claude, which was a model created by Anthropic that illustrated some groundbreaking research they did on sparse autoencoders. Golden Gate Claude, if you're not aware of it, was a version of their Claude chatbot that was obsessed with the Golden Gate Bridge. So if you talk to it about itself, people said it almost seemed like it thought it was the Golden Gate Bridge. It's more like it just was always going to talk about it. So if you asked it to give you a math problem, it would give you a math problem that involved the Golden Gate Bridge. And the way they did this at a very, very high level is they used a technique called a sparse autoencoder. So you've got your large language model is kind of a patient, and we've got this thing, the residual stream, which is what we talked about earlier when we did the imaging. That's basically those hidden states we were looking at. And we have another AI technique called a sparse autoencoder look at the residual stream and try to turn those into interpretable features that are distinct and independent from each other. And it turns out there's a team of folks led by Johnny Lin and Joseph Bloom and some others at neuronpedia.org. You can go to that website, and they have mapped out the sparse autoencoders for various open source models as well. So here's one that they found in GPT-2 small, which is our patient. It is number 7650. And this feature in the sparse autoencoder is obsessed with anything Jedi or Star Wars related. So you can see here, those are the types of things it activates on. We can take that and turn that into a vector. You can think of this as inside back to our map of words, there's a Jedi vector. And if I add it to anything, it makes it more Jedi in the Jedi direction. So what I have here is in this one, I have a version of our sheet where I've taken that feature and I've turned it back into a vector, this Jedi vector you can see here. And I've added some code that at the start of every block, there's a copy table. So this is a modified copy table block. And right now, when you normally run it, the predicted word is, we scroll down. For the prompt, Mike pulls out his, well, it says phone. So let's go back to our Jedi vector. And if I can spell, there we go. And we're going to turn this from true to false. So now it's going to, the original version just simply copied back a table over. Now what we're going to do is if you're block, other than block 2, we can do the same thing we did before. But if you're not block 2, we're going to grab the Jedi vector and we're going to strengthen it right here with the strength. And then we're just simply going to add that Jedi vector to every single token other than the last one. And then do that only in block 2 to see if we can actually change its thinking. So let's do that. So now we've done that, and now we need to reset and run the model and let it go. So this is the model running in action. On my machine, it takes about anywhere from 1 to 2 minutes to make its final prediction. It actually run a little faster than that. I've just added some things that pause between the runs of each cell, just so it's a little easier to watch. I should note there's multiple ways to do this kind of modification of the model's thinking without prompting. One of the earliest techniques, I believe, was called attention steering. What they did was a much simpler thing than a sparse autoencoder. They took the word they wanted to emphasize, like, say, the word Jedi. They ran it through the model, and maybe they'd go at block 2, and they just pull the result of that hidden state for Jedi token out. Then they'd find something they want to clamp down and, de-emphasize, like in this case, phone, because we don't want the prediction to be phone again. And they would run phone through the model by itself. And then they would take the result of Jedi in block 2 and Jedi in block 2 and then phone in block 2. And they would subtract them together. And that would give them a new steering vector that they would inject into the model. It turned out to work occasionally, not as reliably as the sparse autoencoders, but it's kind of one of the first ones of these. There's another technique that uses principal component analysis, or PCA. And that's actually a tool that's very often used for visualizing these large embedding spaces. But they use that technique in order to find the reasonable vectors that might alter the thinking or monitor the thinking of the model. So one of the things they did in that paper was they were able to use PCA techniques to look at the model while it's thinking to actually determine when it's hallucinating or making errors or making bugs. So it was another demonstration of a similar technique. Okay, here we go. Mike pulls out his, what's the predict token? Went from phone to lightsaber, right? We moved everything to the Jedi space. And so now instead of a phone, it makes more sense. Mike, if he was a Jedi, would pull out a lightsaber. So we have done it. We have built the world's first GPT-2 Jedi who said droids can't wield the Force. But more seriously, the message here is you can grow your AI skills by sharpening your mental model of what's inside the black box. There's really 3 reasons you want to do this, even if you're just prompting the models and you're not, a machine learning engineer. The first is to know your tools, right? You build a better intuition for model behavior, better sense of where the limits of the model are. Another one is that this field is moving really, really fast. And if you're going to try and interpret and understand what the latest developments are, or if what vendor claims are and whether they're credible, it helps to be able to, go through a paper and maybe not understand in complete detail with all the formulas, but at least get the gist when they say, oh, we've swapped out, the layer normalization with one thing, or we've swapped out the attention with some other form. You at least want to know what they're talking about and whether it even seems reasonable or plausible. And last but not least is very often as web developers or as developers in general, we are very often communicating with non-technical stakeholders. And if we're communicating with somebody who often has a view that this thing is magic, it can lead to misunderstandings in terms of its limits and its behavior. And if we're able to explain it more clearly and more precisely, we can clear those up. Let me give you a couple examples. So we talked about the theory that LLMs are basically next token predictors. I really love this metaphor from Andrew Main. He was at OpenAI, one of the first prompt engineers, but he said, the LLM is basically like the guy from Memento. If you haven't seen that movie, that's the one where the guy writes stuff on his body so he can remember what he's going to do. And his point is that, when the LLM sits there and it's putting out the next token, no matter where it is in putting out the next token, it doesn't really remember what it was doing. It kind of wakes up, looks at the last few tokens, and it's like, okay, what was the most plausible thing I was talking about that I could complete the sentence with? A concrete example of that is some model providers, this one is taken from Anthropic's APIs, allow you to put words in the LLM's mouth. So here what they're doing is they're trying to extract some structured data out of the model from free text, and they want to turn it into JSON. And what they did is they allow you to pre-fill with an open bracket. So the model wakes up, like normally it would have said, okay, here's the results, right? And you want to get rid of that. Instead, they pre-fill in its mouth the symbol for open bracket, right? So the model wakes up and it's like, okay, what was I doing? Oh, I must have been talking about JSON. Let me make sure the next thing I talk about is valid JSON. And it kind of helps guide the model towards outputting JSON. Another thing you might have heard about is chain of thought prompting. One way to look at this and interpret this is if we go back to our diagram of the model, you note that every step here is basically taking a fixed amount of compute. In fact, the number of times we go through this is very fixed. Actually, the reason this was implementable partially inside a spreadsheet is because there's fixed compute per token. It's one complete pass, everything gets hit. And so that's, good for implementing a spreadsheet, but it's bad if you're dealing with a problem that needs more compute or more thinking because it's especially hard. And one way of looking at chain of thought is what it's really doing by giving more tokens. It's giving it more compute it can spend on the problem, more hits of attention that the tokens can look at each other and actually figure out what the right answer is. So, for example, if you're going to go to a model and ask it to say, do a marketing plan, don't just ask it to generate the content. Maybe put in some sample content, maybe your favorite content, and actually don't even ask it to clone it. First ask, hey, what are the value propositions? What makes it great? And what you're doing is you're stuffing into the context more examples for attention to look at, and it will pull that context back out before you then go and prompt it and say, okay, now generate something. Okay, here are the references for everything I talked about today, so you can check them out. But congratulations on graduating our AI brain surgery school for December 2024. If you want to dive in deeper, I do have a class that I teach where we go through in basically 1 to 2 weeks every single step of the model. You'll see in precise detail how it works. You do not need to be an Excel wizard. You don't even need to be a web development wizard. This is really built with very simple JavaScript. And we walk through the entire model We give a lot of, I like to call them tangible or intuitive reasons for why things work. We don't get into a lot of math. And then you get to see in precise detail how the model works. I've even got students who are taking it now and they're implementing it GPT-2 inside their favorite programming languages because of all the detail they were able to do, and they found it a lot simpler to understand. Special for the CFE audience is I have a holiday promotion code. If you sign up in the next 7 days, you will get a discount. So check it out. And I just want to leave you with where we started, which is hopefully you've got a better appreciation where you're no longer this deer in headlights when people are talking about how large language models work. And you hopefully have this feeling that maybe you don't have complete mastery of the model, but that complete mastery of the model is within your grasp. It's not harder than all the other things you've probably learned as a developer before. And it's totally something you can accomplish. Okay, that's it. Thank you. Now I'll do Q&A.
That was awesome. Honestly, like that was, I'm gonna say, the best explanation I've seen of an LLM, and yet I feel
Oh,
like I
thank
got to
you.
go back and rewatch it, because I'm
I
like,
do. Yeah.
yeah, I didn't. Some of these concepts have to take a little bit to sink into my brain. Um, but yeah, I don't think I understand. I already feel like I understand it better. But yeah,
That's
there was a
something
lot of.
I often tell my class is like the first time you walk through it, I want you, that's when I use that phrase. Don't feel like you're going to get full comprehension right after the end of somebody showing it to you. You'll get full comprehension. You get the feeling that full comprehension is within your grasp by going back and looking at the video and going back and playing with it, right? That's how we build a mental model, is by interacting with something. And that's why tools like this or the spreadsheet are so helpful, hopefully.
Yeah, yeah, no, definitely. I'm gonna go mess with that spreadsheet. So we did have a couple audience
Yeah.
questions, and then I'm gonna open it up. Just like remind everybody, we are here to answer any questions at this point. So if you have any questions, put them in the chat, and I will continue to ask them. So one person asked, why 768?
Yeah, I get that question. I think every class and every time I do this talk. Um, the answer is entirely empirical. That when it's what's called a hyperparameter, it's a number that the model designer essentially picks. And what they're trying to trade off is if they make that number um, too big, then it becomes a lot more computation. So you saw that the matrix, right, in embedding, it was token embeddings, right? You saw that this was 768 long, right?
Mhm.
Row 1, column 768. If I make this matrix, if I decide to have an embedding that's twice as big, I've doubled, actually more than doubled the number of computations I have to do in every single step. And so it basically your memory and compute get worse. But I get more expressive power because you can imagine I've got more dimensions in that space where I can more precisely put those words and get better, closer relationships, be able to find better, more valuable relationships. So it's a trade off, and the model designer needs to pick it. GPT-2 small picked 768. There's other versions of GPT-2, like GPT-2 large and GPT-2 Excel, where the number is much larger, or maybe up to 1,000. I think Llama, for example, is something like 16,000 in its embedding dimensions. So, today's models, because they have more budget to throw more compute at it, will have a larger number of embedding dimensions. But I will say GPT-2 is a popular model among mechanistic interpretability researchers because it's so small you can kind of do experiments really cheaply and quickly on it. So
That makes sense. So I mean, so obviously, like I'm trying to like even
yeah,
picture how this all works. It kind of reminds me many, many years ago, just like basics, like implementing search where you're trying to do like a search that was like trying to find something related to what they put, but it wasn't like so you could search not based on like kind of the the words kind of similarity of words and things like that. So I implemented like an algorithm once to like did some search things that didn't literally interpret the words. It just looked at like similarities in words and then predicted
yeah,
some kind of things like that. Which was, I guess, to a very minor level kind of what they're doing. They're mapping things out and kind of finding the relation of these words and then trying, but on a much grander scale.
Yeah, actually, it's I would say minor in scale, but majorly similar in terms of concept.
Yeah.
One way, like what you described, is is like a classic recommendation system. So you
Yeah.
probably maybe you've heard of like the Netflix challenge, right? And you build this large matrix of what movies a user likes, and you compare that to another user. And embeddings are essentially doing the same thing. In fact, in my class, one of the exercises we do in class is we build our own embeddings. We take like a couple Wikipedia pages and we map them out by just looking at, their how often they occur with other words. And that's basically what it's doing. Just like we look at movies that people like and other people like the same thing, we look at words that occur in the same context. There's this is called the distributional hypothesis. There's a phrase you might have heard when they talk about embeddings. You will know the meaning of word by the company it keeps, which is the idea that similar words tend to occur in similar contexts. And that's how it actually figures out how to relate the words together in that map. But yeah,
Hmm.
very similar concept.
And so tell me, how does it work when somebody does, like when you showed, for instance, re-injury and reindeer? How does that work in terms of like it's not obviously mapping the anything related to the concept. It's
No.
yeah.
So what's happening is it's really a compression algorithm.
Hmm.
And there isn't like an a priori way you can understand how it's going to break the word down, other than to know what it's doing is imagine it took all the text on the internet and it said, I'm going to compress all the text in the internet into 50,000 characters or 50,000 tokens. What would be the least amount of tokens I would need to represent? Imagine this large dictionary of all the large corpus or body of text of everything on the internet. Um, and so words that occur very frequently get their own token, which is why Mike is quick, he moves. Those are all very common words. So they all get their
Hmm.
own token because they're really common, because it's most efficient if that word occurs often to get its own token. But if a word doesn't occur a lot, then it's going to say, oh, I need to break this up. And then it'll break it into the most efficient subword units it can find to represent that word. And in the case of re-injury and reindeer, it just so happens that the way those words are constructed, it's more efficient to represent them, as three words in one, three tokens in one case and two tokens in the other. And I want to be clear, this is about what's the most efficient way to represent it in the whole corpus of text it was trained on. It's not how to represent it efficiently in the prompt you give it. That's a really
Hmm.
important distinction. So it because what it's trying to do is compress all the text on the internet that it's going to then put into training. It's trying to compress the amount of work it needs to do during the training process. And we're just trying to
Hmm.
translate it back into that new language it created during the training process. So it's hard to kind of intuitively describe what it picked. It happens to pick, linguistic morphemes, just kind of not completely by coincidence, but it's like correlation. Like, est on the end of words or ize on the end of the words is very common. So it's not a surprise
Hmm.
it's going to find it. But if there's a suffix that's less common, it may not find it. So re-injury is a great one. It didn't pick the re, it decided rain was more common. So hopefully
Hmm.
that helps.
Yeah, it does
Like
help.
we go through the entire thing in detail. It's usually like 45 minutes or so to go through like the entire model, and then as part of an exercise we work through like manually doing it.
Hmm.
uh, but and it gets hopefully a better intuition for basically how it did the training and then how it breaks it apart. But that's the best kind of high level intuition to think about it, is it's just looking for the most common subword units and using those.
Awesome. Okay, that makes sense. And the other question we had was just, I think this was related to your spreadsheet thing. And
Yeah.
I'm gonna assume the answer is no, but somebody asked if it's open source on GitHub. Um,
What, the website
the
or
or the
the
yeah the spreadsheet that you built, that the yeah your web the GPT-2 web page that you
the
built.
GPT-2 webpage? So, well, first of all, like I have a class that is paid, but
Yeah.
I kind of am giving away software is kind of what I say, and I monetize on the content. But um, the spreadsheet is available for download on GitHub.
Oh, okay.
The Yeah, so you can just go to GitHub. Spreadsheets are all you need. You can go to releases. and you can download, the old spreadsheet that runs in Excel. The website itself, I'm planning to open source the framework that I use to build it. I haven't figured out what the license is going to be, so I'm basically still figuring that out. Um, but for and then whether the actual page itself is open source or not, I'm still basically deciding.
Hmm.
But for the purposes of like teaching and exploration, like I wrote it so it was readable. Like you saw me stepping through it. I'm just trying to figure out what makes sense license wise. But that's like you can go. It's a web page and it's been written in a way that you can step through it, and you'll see comments in there. And I'm planning to go back and make the comments more readable for a reason, because I want people to be able to play with it. So I don't want to inhibit that. I just haven't figured out which parts get open sourced and where I draw that line and what the license is. So that's a TBD, but I very much want this to be used. So I'm figuring that out. In fact, if people have feedback on the license they would like to see, let me know. So I'm all ears. Reach out to me on, I'm on LinkedIn, Twitter, Blue Sky. Ping me. I'd love to hear what people think.
Awesome. Okay. Yeah, that was he clarified that that is what he was asking, the JavaScript implementation. So yeah, Dan, you can reach out to Ishan. All right, that was we're running out of time here, but that was actually fantastic. Like I said, I really do want to go back and rewatch it. And your class sounds fabulous. So
Oh, one thing on the
yeah,
class I should
yeah,
note is, your company probably has a learning and development budget for those of you guys watching. And this is usually applicable to that learning and development budget. And in fact, we're at the end of the year. So your learning and development budget is probably going to expire if you haven't used it by the end of the year. So this is something that you're like, hey, I can quickly, and you can say, hey, I'm going to be a more AI savvy engineer at work. That's certainly going to be helpful for the organization. So another way to think about when you see it is, hey, it's a great way to use some budget that might disappear on New Year's.
yeah. Great idea. Okay, so thank you, Ishan. This was really good. And thanks to everybody who joined live. I really appreciate you. I hope you have a happy holiday, happy New Year, and look forward to seeing you all in the new year. We have a lot of stuff planned. I'll be coming out with that soon, so keep an eye on the site. And as always, you can reach out to me if you have any questions, comments, or feedback. So I'll see you all in the new year. Bye.